my screen?
Say yes.
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 Okay.
Okay. Hi, everybody. Today I will talk to you about the RNA-seq, how to analyze them in Galaxy. I will not make it big, the screen, because I will jump into the other tabs quite frequently. So let me talk a bit about Galaxy. It's a web-based platform that we can process biological data, perform several analysis to the biological data. And it's open for everyone. And you don't have to know programming before using Galaxy. So it's a biologist friendly, so everybody can use it. That's why it is good. And yeah, we will analyze some data today. Our data analysis workflow will be like, first we will extract some data from NCBI to Galaxy, and then we will talk about I will talk about the I actually didn't show it in here, but a quality control to see the quality of the data. And then we will do alignment. We will map the reads to the reference genome. Then we estimate the abundance of these reads, mapped reads, which genes have how many transcript mapped to them. And then we do differential expression, and then we do some annotation. And then I will go to Galaxy. Yeah, this is my Galaxy page. So
So sorry, you just went to usegalaxy.org. That is the address, no?
Yeah. I'm using Galaxy.org, but there are like 3 Galaxies. This is the US-based one. There is a European one, Galaxy EU, and there's an Australian one. So I have actually account in this one, but also in European one because of the space issues. Galaxy actually gives you like 250 gigabytes of space. So I was running out of space, and I opened an account in the other server. So yeah, you can basically use any of them. They have the same tools, I guess. So this is my history. This place has all the things that I do. It kind of jobs kind of queued in here. If it's like complete, it looks green like this. And you can kind of change the name of the history in here. And you can kind of add some tags to your history here. And you can have multiple histories. Like if I click here, you will see my all histories. Like you don't have to do everything in one history. You can like separate them in several histories for several analysis, because Galaxy is not just for RNA-seq analysis. It has various different analysis. To be honest, I only know the RNA-seq analysis in here, but like text manipulation or like variant calling, something about SNPs. And there is even today I found that there is machine learning. That's interesting. So you can perform several different things in here. Something in the chat. Yes, it does everything. Yes, exactly.
Except writing the thesis. That part
yes, yes, I have to do that.
Everybody has to do it.
Yeah. And this place it has the tools that we use. We can also search the tools in here, and let's say that let's open a one tool. When we open it, we can see it in this main area, this tool. Today, I will upload a data in here. We can actually choose local files or paste and fetch data using URL. But today I will do a different approach, and I will do SRA accession number. In order to find that, I will go to a geo page of an RNA-seq experiment. This is like a typical geo page, you know, the samples and such. Normally in a microarray experiment, you know, the cell files would be down here in the supplementary files, but for the RNA-seq experiments, there is this link in here which will direct us to the SRA run selector. SRA is sequence read archive. It was previously short read archive, and then they change it. This is like the depository for all the sequence data, like people do sequences and then they kind of dumped in here so other people can use. And in here there are like information about this experiment, and down here we have the samples, and you can see the they're kind of big. It's not like the microarray experiments. Every sample is quite big. You know, the total is like, let's see 60 gigabytes. So in order to fetch the data, I will copy the accession number of the sample. I will copy this, and then with my Galaxy. Yeah, I will paste it. Let's paste another one. Yes. Now I will start it. Yeah, now it's queuing. This actually will create a text file that contain the accession numbers. Then we will use this with a tool that is called Faster. Yes, faster download and extract reads in FastQ. Yes, this is a tool to kind of extract the data from the SRA, so we can perform different types of calling the data from there. Like we can use a single SRA number that I can paste the one that I copied from the SRA, or we can use a list of SRA like we did in this paste entry. Actually, I should every job that I'm kind of jumping, but we do in here, if we click the name, we can see the details about this this element in here. It's like it's a text file, or you know, we can download it, or there are some, you know, the details. If I click details, it shows the details over here. And if I see the content like in a whole page, I will click this I and I see this, yeah, in here. Let's go back and we will do list of SRA, and the past entry element is in here. So in order to call the data, I will just press execute, and it will create this 4 elements. Now this will take a bit time, so we will not wait for this. We have it in here. It's like a cooking show. We already did it. Yeah. Depending on how the experiment is executed, whether it's a pair end or single end, one of them will be full. Our experiment we're using was a single end. That's why this one is full. you know, this has these are like the samples, and we see the details, and it's a FASTQ Sangar file, and we kind of see it. Yes, this is like basically a typical FASTQ file with the sequence and the quality scores. After we downloaded the data, after we extract the data, we will perform the quality, and we will use FastQC tool for that. Yes, in here. In here, you can actually enter a list of adapters, but I will not do that. And I will just, was this the tool that I was using? Oh, yes, in here. Yes, I have to choose the files in here. Yes, since in our history, the single end data was full, I will choose in here. You don't have to put anything in here to do the quality check. So you will also do like an execute. And I will show you the results of that in another, what I did before, the quality, if I did before. Let's see. Yeah, it will produce this two output raw data in the web page. Web pages kind of looks like this. Yeah. And then, you know, it's like the basic statistics and the, we can see the quality in here, you know, in this experiment, the quality is quite good. So, you know, we don't have to do anything, but most of the times, you know, if you're downloading something from internet, qualities are good. I'm assuming people not just throwing their data, maybe they're also doing, they're refining the data before uploading. So actually, if we do this experiment, we might get some bad quality. So I will show you a bad quality sequence. It was something like here. I found it on internet. It is actually called bad sequence text. Yeah. As we can see in here, this is like a really bad quality at the end. And there are like other things like the overrepresented sequences, like the sequences were overrepresented. And sometimes, you know, FastQ can kind of see that where it might be, you know, the contamination, you know, it kind of recognizes it. So what we can
I want
okay.
to make a couple of comments. First,
okay.
I don't know how much we need to explain. I mean, how much people need to know
quality.
And I mean, the point is that everybody understand what is here, or shall we explain a little more what we call quality here?
Can I also interrupt for us? There is documentation for this page that goes over every one of these summary sections, and that also explains what may be the cause of it. So if it goes in for the per health sequence code, for instance, it goes if there might be a bubble in the sequencing or in the per sequence GC content, there might be a contamination by other organisms, that kind of thing, or the library preparation. There's a very nice document for it.
Yeah,
in this site.
So you don't need explanation. That was offering the explanation. So okay, if you don't understand, you ask Barish. He is the expert now.
Yes.
So, but I have a comment here that first we are speaking here the quality of the reads, which derives in, well, includes several things, but start with the quality of every base pair. Is the quality of the sequencing, no? And in sequencing, quality is something that is well defined. It's essentially something like the log of the probability of error, or proportional to that. It's an integer number, 10 times the log in base 10 of the probability of error, something like that. And here you have a comment. This is the Illumina. That was the adapter. That was the primer. So here you say that you're not putting the adapter. That's fine for a class, but in general you may have the issue like they have here. That and in my limited experience, sometimes the overrepresented sequence are indeed some adapters that some non-standard adapter, but you realize that the overrepresented sequences you can also see in the per base sequence that they tend to be overrepresented at the beginning, for example, of the sequence, suggesting that you are seeing the adapters. Well, that's my comment. That this is something that is beyond gene expression. This is about sequencing in general. So if you are doing a genome assembly, you are also doing this thing. Fine.
Fine.
No. I know that you and Baris are fine. Just looking at Tunç and Ramal and people who are not necessarily seen this. I mean, Ramal saw it because we spoke about this in class. Well, that was my comment. Okay, I give you the microphone back.
Okay, I talk about the FastQC because I can show some tools to how to tackle some of the issues because of the quality. Like we can trim or clip the sequences to make it a bit more like a good sequences. And we have a tool called Trimamotic. Yeah, we can actually put the sequence here, like in our history, we have the single data set, we can put it. And we have different options in here, like we can cut a specific length, or we can, cut the start of the sequence, like we can like say like 15 from the start, or we say like cut 15 from the end, or something like that. And we have another one, which is called, let me check my thesis for that. For the adapters, cut adapt. Yes. We can remove the adapters, like overrepresented adapters like this. We can like select in here our sample, and then like we can insert an adapter, and we can actually choose a standard one, a built-in one, if we know it. But if we don't know, we can enter like a custom sequence, like we see it in this batch sequences. Like we can cut, we can like copy from here and paste there, so that it will cut for us, this tool. So after the quality and the cutting and the clipping, we will do alignment. So for that, I will use HiSet2. There are other alignment tools like Bowtie 2 or something else. Actually, there is a alignment section in here, or mapping. Yeah, there are like different ones that you can use. I use this one. So in here, you have to have a reference genome. So I will not upload my own reference. I will use a built-in one. And I will choose human because the experiment was conducted in human. This is kind of important. I think I used this one. I used in my previous analysis. And then we specify in here how the experiment was conducted, if it was single-ended, pair-ended. In our case, it was single-end. So we will choose the data in here, like, and then we can specify if it's stranded or unstranded. And then we executed this one. Yeah, this is still goes on, as you can see, you know, because since these are big files, it is taking a little time. And also assembly also takes some time. And I will show you an aligned file, my previously aligned files, one of them. Yeah, in here we can like click in here to see how the alignment file looks like. These are like the comment lines. The actual file is kind of starting down below. Yeah, these are like the showing the position of the reads and their kind of where they came from, which chromosome they came from. I don't even understand basically. It's to me it's like just a kind of middle step to the other analysis. This is actually this. Sorry, I didn't specify that, but after the high set, this tool produces BUM files, which are like binary alignment something files. And after we align this, I mean, it is not completed in here, but if it's completed, it looks like this. After the alignment, we will do estimation of the counts. So we will count how many reads map to one gene. So I will use for that future counts. There are also other counting tools you can use. I'm using this because this one actually has a built-in reference genome, gene annotation file. In other ones, you have to kind of provide the gene annotation. And sometimes this can cause problems, you know, your genes may not be annotated. Yeah, you can, as you can see, I mean, it is not completed yet, but we can still use this because it is like a pipeline. So we can, we don't have to wait it to finish. We still can use it before it's finished. So we specified some of the things like gene annotation file. Future counts has a built-in annotation in here, like a human 38. And we can click and execute this. I will show you. We have a previously cooked one. Yeah. Output of the future counts looks like this. These are like basically a tabular file for every sample. It is annotated by interest ID, and then corresponding to every interest ID in here, kind of how many reads map to this gene we can see in here. Yeah, we have one for every sample. And then since we now have the counts, we can go to the differential expression and a tool that we are already quite familiar of, which is Lima. Yes. We can provide a big matrix, like a count matrix for every sample, but kind of in Galaxy, for every sample there is a count file for every sample. So we will kind of use the separate count files. Let me kind of change my history. Yeah, we will provide several count files. And in here, we have like, let's say we have factor like a treatment versus control. Let's say treatment. We can insert another factor in here if we have one, like, I don't know, maybe like different species. If we conducted like for every species, one treatment, one control. In here, like under the factor, we have like group. This is like control. Let's say control versus treatment over here. And controlling here. Yeah, now we have to choose our file of future count outputs. Don't have it. Yeah, in here. Yeah, you have to kind of know which of these samples corresponds to which condition, like which one is control, which one is treatment, so that you can choose like correctly. Because once you upload it, you cannot differentiate it. There has to be future counts, yeah. Yeah, these are, I think, like you can choose in here if you know, and you also choose control in here. Let's say like this is a mock test. Yeah, let's choose this too. And then you can provide a gene annotation, but I haven't provided one in my analysis before. I didn't put a contrast information file. We can put it actually, but we can also create the contrast in here, like we said what in here, control and treatments. We have two controls. Yeah, if we set it like that, you know, the exact names. If we want it like contrast for control and treatment, we write like this. Yeah, if we I mean levels more than more than two, we can like control treatment 1, treatment 2. We can make like control versus treatment and control versus treatment 2 in here. We can add multiple contrasts in here. After we did that, we have a section for filtering the low counts. This actually, you know, doing this kind of improves the number of the differential expression genes, you know, I found in my analysis. So when we say yes, we can, you know, choose either row counts or the counts per million option. If we choose like counts, I mean, we can specify like one count, let's say. The threshold is like generally 10. I don't know why they use it 10, but most of the forums that I checked, they kind of suggesting the 10. We can either do a total count, you know, filtering by total count, like counting all the row count numbers of the samples, you know, summing them after that filtering, or you know, we can do it sample by sample, like here. And then in here, we can use the output options, because the Lemma provides us with a differential gene expression table, and then we can actually, if we want, we can click the yes for filter counts or normalize count, or we can even generate an R script file, or we can, choose in here which kind of plots we want to see in the report, because Lemma kind of produces a HTML reports in the analysis. So in the end, we click in the execute, and this will create something like this. I will show you. Yeah, this is like the outputs of Lemma, the differential expression tables. We can see it. Lemma kind of produces one table for every contrast. Like in here, I have like multiple contrasts in here, because this one had a lot of different levels in this experiment. So let's see one. We are actually kind of familiar with this because we seen this in R, the log fold change, average expression, and such.
This is the output of top table, no? And
yeah.
what essentially you say is that they are making a top table for every coefficient. The coefficients are the contrast, and yeah. So yeah, it's the kind of question that you will like to. I think that most of the time, this is the thing that we like. And question, what here is showing everything, or just the genes over some p-value, or I mean,
this shows everything. Everything after filtering the low counts. I mean, it is actually filtering that and then doing the calculation.
Yeah, the low count, I didn't want to interrupt, but the low count is essentially that genes that are not expressed, or expressed so little that any minor noise will be amplified very much. I mean, if you have, let's say, 3 in one condition and 4 in the other condition, you increase 30%, but it's just one read. And that one read, the probability that exists or not exists is very, very small, but the effect is very big. So in general, low expressions are noisy. I mean, I don't know if you remember when we plot this banana plot, in the low concentrations were always more spread. So in general, yeah, when you see something few times, it's very hard to make a conclusion, to generalize. So, and why 10? Why not? I mean, it's a small number. You know, kind of everything less than 10 is small for sure. It can be 20 maybe, but you have to see if I mean, if the gene that appears more differential expressed is something that you have seen very few times, it may be just noise. The differential expression may be noise. Anyway, keep going. Don't interrupt.
Okay, I will show the other outputs of this is the main output of the Lemma, and there is like a report on the this normalization in the differential expression. This is kind of comparing the normalized versus unnormalized versus normalized, plotting them, and then like some showing the kind of variance between these samples, I guess.
I will say more like the correlation, no? Like all the samples
which
that
ones are
go
close
together
to each other.
Yeah.
And yeah, this is isn't the banana shape.
No, but this is simply because here they are measuring the variance. Yeah, but you see more or less what we say, that when the interest that you have count size, They add 0.5, so you never get 0. Sometimes you may have a count equal to 0. They add 0.5, so the logo is not a problem. And you see when the count size is small, the standard deviation tends to be high. And when you have more count size, the standard deviation tends to be smaller. So again, very low counts are noisy.
And like we have volcano plots. Somebody saying something?
Yeah, can I ask a question? So each dot represents a gene, right? And can you go up top a little bit?
Okay.
So a bit more. There were SRR numbers just on top, a little bit more on top.
Yeah, this one.
These are you entered, I think, 3 SRR.
Yeah, I'm showing what I did previously.
Okay, so there was more.
Yeah. This one has like 30 samples.
Okay.
I'm showing you what I did before, because we have to wait for this analysis. Differential expression actually doesn't take much time, but the other steps kind of take some time. So I'm showing what I have in hand.
When you say sometime, you're speaking of 5 minutes, 1 hour, 1 day?
I mean, uploading, extracting the data kind of take like maybe 30 minutes or 1 hour. It kind of depends on the, I mean, if it's like 16 gigabytes, like it may take maybe 2 hours. I don't know.
Okay. No, okay. My question is kind of very practical. Like, do you go for a coffee or do you go for lunch?
You go for lunch. Okay. You go for lunch for uploading data.
Or you run and you went until next day.
Yeah.
There is something I really don't know the detail, but I know that what you say is an issue, and what the people are doing is that they are putting the data already in Galaxy or in some cloud. Either Galaxy can access Google Cloud or Amazon Cloud, but there is a way essentially that you don't need to move the data because these are public data. In this case, I mean, if you're using your own data, then no shortcut. But if you are using public data, there are or there will be soon ways to avoid moving the data.
Yeah, that would be really, really nice. Because it takes so much time. Yes, I'm continuing. Okay. So we have the differential, like a contrast. For each contrast, we have like a volcano plot. These are kind of the showing the differential expression. If it's like further, they are like more expressed or less expressed. If we go down here, and there's like a plot for every contrast. Like in the end, we can see for each contrast how many genes go up and down and flat for this case. Yeah, it's like we can see like which sample corresponds to which condition, so we can like check in here. Yeah, this is like the report, and we also have this is like a filtered count and normalized count. If we only want the normalized counts, we have like the single matrix for every samples in the column, and then we have of course the gene ID.
Do we know how they normalize?
Yeah, we know how they normalized.
I don't know. So
The Lima use TMM for default. But we can actually choose in the advanced section the type of normalization we want to use. Let's kind of check that. Yeah, I think this advanced section. Yeah, normalization method is default TMM, but we can use the other. I don't know these ones. We can even say don't normalize. Yeah, there's actually one interesting thing about the waiting period. Since I am registered in here, and if you want to use, you can register. You can click the email notification. When the job is done, Galaxy sends you an email, so you can know if your job is done. So differential expression is basically like this. After this, in this processes, since we in the future counts we annotated the genes with the interest ID, but we might need more information about the genes, like we might need the ensemble IDs or some other IDs. So we will use the interest ID knowledge to extract the other information. Like we can use any tabular file. Like let's see, is this a tabular file? Like with the, you can see like the gene IDs over here. Yeah, I will use this one. This was the last one. We will specify some of the things, like file has header or not. So let's say yes. We will specify the organism, and we have interest IDs. So we will provide this, and we can choose the information that we need, what we want, you know, the ensemble ID, symbol, or gene name, or ontology, or alias. We can choose this, and then we execute. This will.
So this depends on the annotation that you are using, no?
Yes. If you're using like interest, we used ID type in here, like the interest.
No, but my point is that the different version of the, let's say, human genome. I mean, obviously, if you are using human, you cannot use an annotation of mouse.
Yes.
But even in human, there are different ensembles, different versions of the human genome, and they may have different genes, different. And the other point is that you should guarantee that your BAM is using the same I mean, the alignment that you did using the same version of the human genome that you're using for annotation, no?
Yes, absolutely. But it's not a problem most of the time in interest, but in ensemble.
Yes, because ensemble does the annotations based on the genome version. So they annotate the transcript sets and the gene IDs based on the GRHA 37 or 38. Yeah, that's I don't know why, but that's the thing.
Yeah, thank you. Good to know. Yeah, the output of this file, as you can see, like we provide the interest, and now we have the ensemble equivalent of this, and the symbol, and the gene name of this, and you can see some of them doesn't have ensemble IDs. Yeah, we can annotate this.
A comment.
Yes.
So, I mean, Baresh knows everything, so he can answer that. But everybody know what is interest and what is ensemble here? What do we mean by this?
Yeah, I think so. The interest is where you get the NCBI ID, and ensemble is the other database that stores the nucleotides and genes.
Yeah, I think you are not wrong, but I will not say it that way. How I understand is like interest is the query ID for NCBI. You are right, and ensemble I think is for the European for AB. So it's kind of the American version versus the European version. That is the big picture. But then there is something else that kind of runs in my mind that NCBI had two versions of calling objects. The old version, they had a number, like the number that we are seeing, and they call it the gene bank ID or GI. And eventually they move it, they run out of numbers. They say, okay, we are not going to do it anymore. And they say, from a couple of years ago, they say, from now on, we are not using GIs anymore, we're using accessions. So NCBI has two names for them. And accessions are, like I say, a little more stable, because one of the decisions that the NCBI made at the beginning is that every time they see something new, they put a new number. So if you have the same gene in a different version, it's a different GI, a different, so things change every time. And that apparently was not such a good idea. It's better to have kind of the same accession, and the accession include a version. So you have the right to update it, but it's not automatically updated. I mean, it is easy to see the different versions. With GIs, it was a mess. I mean, you have to look in a database. But okay, everybody understands that one is the American version and the other is the European version, no? Okay, great.
Also, one little comment, ensemble is ANS for the, I am guessing, ANS for the Institute of Amble European Molecular Biology Laboratories. So ensemble.
Yeah.
Yeah,
you're right. You're right. You're right. You're right. I didn't. It's just that I always think about the ABI, the European Bioinformatics Institute, but they are part of the MBL. Yeah, you're right. You're right. Yeah. So, but another comment that Cemre showed, and it was in fact a problem in her work, is that things have two names. I mean, no, sorry, no. Things sometimes have one name in one part and not name in the other. The equivalence is not 100%. So we have cases that a gene existed in one version and not in the other, and other cases in the same gene had two names in the other. So
when we get rid of the ensembles, problem was solved.
yeah. At the end, we got to use a coherent version, the only one, but it was a headache.
Yes.
I have a question. If you, I was wondering why you choose by going by the genes and not by the transcripts. Is there a specific reason, or?
Using the transcriptional data, you say?
Yeah, but annotating the transcript instead of genes, and counting, feature counting by transcripts and normalizing by
because we have to use in machine learning the genes. We needed the genes to kind of, I don't know, annotate them. I mean, we can say that a transcript is a target. We have to say like the gene is a target.
That I think it's a interesting
question. Yes.
Yeah, but I mean, what do you call it? Well, okay, I know that we have in NCBI in ensemble you have the ANSG, which means gene, and NST, which is the transcript. In this case, I guess the point is one has exon and the other doesn't has exon, no, that or introns. That is the difference, no? Is that the difference, or is anything else?
Just because of the transcripts might be some same gene might have different transcripts that
exactly
you may have
alternative splicing, and you may have more than one transcript from the same gene. And then the question is, do we want to count every alternative splicing as a separate thing or as the same thing? I think that is the question, no? But, I mean, there may be another point that may be interesting, is like if we are counting with introns, then sometimes some reads may not match because, I mean, let's say that the read contains the intron, so it will not match, may not be aligned correctly. I don't know. It will be interesting to know.
But because of transcripts, they won't have the introns.
Yeah,
but
exactly.
Different versions of the same transcript that may, for instance, in previous study, there was a gene called EEFD1. That's the elongation factor that works in the protein translation. That has two versions of it. That one transcript is shorter and one transcript is a longer than, that has a different exon, that longer exon. And that long version works in the development, and the shorter version has a heat shock, works in a heat shock scenario. So that make different versions of the transcript has different biological effects, and that may change on the maybe this treatment on case effect instead of just by the gene. I don't know.
Yeah. Well, as Cemre said, in her thesis, the object of interest was the gene. But it's a valid point that we could have go to the transcript, and if you have several transcripts from the same gene, you can back map to the gene. But I am guessing. I am guessing that the result is not very different in this case. I mean, as you say, there may be two objects that we are calling with one name. In this case, we care about the gene, not about the different track. So there is only this marginal case that we may have some reads that did not map because were covered, they contain the intron, let's say. Or that may happen, and I don't know how much it happened. But my guess is not a big percentage. It will not. I mean, more exactly, there is some chance that that will happen, but that chance is independent of the condition. And since we are doing differential expression, that noise that we may be missing some counts, but the probability that we miss in every condition is the same. So I don't, a priori, we don't, I mean, of course, to have a complete answer, I have to do it and compare. But a priori, I will guess that it's not a big deal.
Yeah, well, it might be after when we are interpreting the output.
I mean, there is, if you go deeper, the question is why our interest is the gene and not the transcript. And that I think is a valid question. It's valid because I don't know if you saw, Tunç saw the presentation of Cemre in the conference last week or 2 weeks ago. But the basic point is that we are looking for targets of a pathway. And we define a target as genes that are, but it could have been. I mean, the point is literature. Since we are using a machine learning method, and we need to give you some examples, and the examples are described as genes. I mean, in the literature of the topic, people describe genes as target and not transcript as target. So. Yeah, even if you wanted, we don't have the info at that level. But you can imagine, okay, PhD thesis. Okay.
Yes.
For someone.
Yeah, he gave us the idea.
Yeah, that's a good question. Any other comment?
I got another comment about the galaxy in general. They do have images of the galaxy itself, so it's just not 3 websites that runs in a different continents, but you can also deploy it to your own beefy machine or a preferably a server that you can use in local.
mean, yeah, you can have a Galaxy at home,
Yeah.
and people can do. But I think what Cemre means is that the public ones, that if you don't have your own cluster, if your cell phone has not enough batteries, you can use it, and these are the ones that you connect and you are free. But yeah, if we were rich and powerful, we can have our own.
I mean, you don't have to keep your computer open for the task to be run. You just click there and you just leave it and it runs.
Yeah, at the end of the day, I think that is the point, that you don't need to install anything. You don't need to program it.
Well, the main problem was with the Galaxy. Well, I joined a couple of months back in a workshop where we were invited to Acıbadem University, and Uğur Sezerman is working in computational biology there.
Yeah.
Well, they were trying to get a patent for a treatment, actually. So if they used Galaxy, Galaxy sends your data automatically to the CDC and WHO. So you're basically accepting that if you're using your data, you're accepting your data will be transferred to CDC for research purposes. So if you're trying to get a new patent for your study, it might get some tricky points on regulations at some point. So he was saying it's better to use local libraries rather than Galaxy if you are trying to get a new patent.
Yeah, I agree with that. I'm not 100% sure if they are sending that automatically, but they can. I mean, I had the same problem in my project. We were also trying to have patents because my project was industrial applications, so we were not hurting anybody. But there's a point that if you are using public services, your sequences, your secret, let's say, your private information is going to the cloud, and you don't know who is there, and they may be. And not only CDC, I mean, I would think that there are many big countries with a big group of researchers that will love to know what other people are doing, no?
Yeah.
We don't say because they will kidnap me, but yeah, the bottom line is yes. If your data is private, if you are doing something that you don't want to public, and one of the reasons that I tend to use my own servers, but the point at the beginning is like, as Cemre said, this is biology proof. You don't need to know. I mean, you can do with the mouse, not with the keyboard. That is the difference. If you use the mouse or the keyboard, that is the. Anyway, but it's better to have it. And I personally like the point that there is a lot of things that can be done in the cloud, and eventually you don't load the script. Like, I mean, in my vision, you have a step in which you are kind of developing the protocol. You know, like, I mean, you probably hear me, but normally the problem is when people start analyzing the data, it's too late to design the experiment. I mean, when you analyze the data, you find that the experiment didn't do the proper normalization, the proper regularization, things like that. So I normally say, do the simulation, do the analysis before doing the experiment. And that you can do with public data. Somehow you design something that is similar, or you simulate data, and you can do in Galaxy all this exploration. And eventually, when you are happy, you are finished, you download the script, which is the protocol, and you can run it locally with your own data at the end. But you don't need to do the exploring of the protocol in your computer. You can do it in the cloud, no? Anything else? So Cesarman was doing a workshop on this thing?
No, it was a week workshop, and he was the last day of have to.
The workshop, but because I mean, I just before COVID, I went to a super interesting conference on metagenomics in Acıbadem. They were doing very good things, and in fact, the following week, they were teaching something, a workshop, and it was too late for me to organize it because I had something else to do. But I am always curious of what they are doing because they are doing very, very interesting things.
Yeah, well, the workshop was about the phylogenomics, so they were teaching us the phylogenomics part, but they were mainly creating patterns, so they mentioned that problem when working on patterns. But in phylogenomics, well, you can use Galaxy or whatever suits you.
Yeah, yeah. I guess it's something phylogenomic. Probably something that you get when you do metagenomics, no?
Yeah.
Yeah. Interesting. Okay. Do we have anything else?
Yeah, I was actually going to talk about the normalization.
Go ahead.
Yes. Yeah. Why we do normalization?
You asking me? You're asking me?
No. It's a rhetorical, rhetorical question. Yes. Why we do it? Because we were I'm thinking like we have apples and oranges, so we have to compare them. So we're turning apples to oranges to compare oranges to oranges. Yeah, for that reason. There are like some issues which are like I said it in here. Some genes are longer than the other ones, and the longer genes tend to have more reads mapped to them, but it is not necessarily means that more gene expression, long genes are more expressed. So we have to kind of normalize for gene length. And the other one is like a sequencing depth, is like you have one sample which is like 1 million reads in this sample, and you have other sample which you have 2 millions of reads. Does that mean that genes in the 2 million reads sample more expressed? No, we don't know that. We have to kind of normalize to see the biology behind the technology we're using. So I will show you the Rpkm normalization, which is reads per kilobase million. It's like the basic normalization, but this is just one of the many normalizations that people use. It's just the kind of giving the sense of the normalization in general. So I will do a small demonstration in here in the Google Sheets. These are like just
you need to share your screen.
Okay. Yes.
We already see the Google Sheets.
Do you?
No, then I am the one that are looking the wrong place. Sorry.
Because I was always switching in the tabs.
You did well. No, I was looking the wrong screen.
Okay, then. For the normalization, first we need to sum up all the counts in the samples individually. Like let's say the sum for this. This is something like I don't know. It's so cool. And we do this like this. Yes, we sum. And now I will scale with 100. Normally in the original one, it is million, but the million is like an arbitrary thing for the number to make the numbers kind of look more appealing, like more understandable. It's like when it's millions, it's kind of crazy, but it's like when it's smaller, we can kind of understand it better. So I will scale. anyway, I will just divide these numbers. 500. Okay. And now we go here. Yes. Now we have the per million scale. Now I will scale all the counts for all the genes and all the samples with this scaling factor. This is our scaling factor now. Like I will divide B position 2.
You have to put an equal sign.
Yes. Yes. And now I will divide this with this scaling factor. I think I will use this B6. Yes. And then
And you need to put $6.
yeah. Yes. Oh, we have it. Yeah. We kind of do this to make the numbers better. And now I have to do, can I go like this? Is it true?
Yep.
No, it's not because. No.
It is.
Is
Double
it?
click.
Yeah.
Click it.
Okay.
Click it. Yeah.
Can I go like that also?
Yes, and down. Yes.
Yes. Now we scale with our scaling factor, but we also.
Sorry, here you get rid of a technical variability, which is the number of reads that you got in the sequencing machine, but that is something that depends on the machine. It's a technical factor, no?
Yes. And this is the second one is, let's say, is it biological factor? We have to now scale with the length, because I said the longer genes tend to have more reads mapped to them. And now we will divide the B6, is it? Yes. B6 divided by E2. I'm dividing this this scaled numbers with the gene length now.
I think you need to put $1 in
the dollar, yes.
In the E.
Here, yeah. Here, and I will go like this. Like this. And I will do the same for the other ones.
I think you can copy.
Going like this, you mean?
Yeah. But you are editing. You stop editing the cell and then you copy.
Like going like this.
Yep.
E3, yeah. Magic.
Yeah, that is the dollar magic.
Dollar magic, yes.
Okay. Dollar sign, okay? It's not the dollar itself.
Yeah, let's make this. Yeah, as we can see it in here, it's like I actually kind of make these numbers up, but it kind of fall beautifully, because we can see in the sample sample 3 gene A, it's like 45 counts, and the sample 3 gene B, it is like 25 counts. I mean, when we look at the row counts, we would say that there is a difference in this gene expression, but when we normalize, they're actually the same. Also, there is like this interesting thing about the gene C, like in the samples, it kind of looks uniform, but after we normalized the sample 3, there was an increase, so we are doing normalization basically for this. I mean, things can be changed, and the raw data kind of doesn't give us the exact thing that we actually want to see.
I mean,
Yes.
that is correct. I don't know if you see the reason why of this. No, it's like at the end, what we want to do is kind of well, the idea of normalization. There is something that we measure, which is the number of reads that fall in every gene or every transcript. And there is another part that we really want to know is that what's the concentration of the messenger. What we really wanted to know. And the question is how these two things are related. And the longer the genes, the longer the messenger, therefore the higher the probability that we read. The point is that the sequencing, the library production, the thing that we sequence, it's a sampling. It's a random sample. And there's, of course, all the theory that say that the samples that we get are random, but not completely independent of the original data. So it is, at the end, the same philosophy, like you get, you make an experiment 3 times, you measure a temperature 3 times, and you are using your samples to try to guess what is the real value. It's always the point that there is a real value that we cannot observe directly, but we observe the indirect consequences, and therefore we try to make an inference. But I have no comment here that in general, we don't compare gene to gene, no? In general, we compare condition to condition, the same gene in different conditions.
Yeah.
In general. Any other comment, Barisis?
So in another thing, why do we first normalize wide read count and gene length later? What happens if you normalize first for the gene length and then read count?
Well, I guess read count makes sense that you are trying to normalize by the technique first, no? Like I think in the formula, we can try, but I think in this formula, they are giving you the same number. You are divided by the two things at the same time. So at the end, the number that you get in the last is, I mean, if you see, there is the result in, let's say, B12, at the end of the day, is essentially B2 divided by B6 and divided by E2. You have a factor in the last row and a factor in the last column, and you are dividing by both things. So, and I think therefore the order is not relevant in this formula. But there is another approach in which you kind of divide by the gene length first, and then you take the sum, because the very first, the part that is not commutative is the first step when you do the sum. I think I don't remember right now. I prefer not to invent, but there is some strategy in which you divide first and then you do the sum. But there is another point that, okay, those are the things that I have to understand before next class. But there is the last point is that when imagine that you have this situation and you have the condition that we see, and imagine that in the last moment gene C increases a lot when the gene A and B don't increase. Let's say that you have two scenarios. The concentration of A and B are the same, but the concentration of C increases a lot. Since we are divided by the total, the concentration of C increasing will, in relative terms, make the concentration of A and B reduce. It will seem like they are reduced. So the more advanced method take that in consideration. At least you can do what you can do there. You can say, I mean, what I'm thinking is this: like you have a limited amount of reads that you can sequence, and if one of the genes, let's say, or a few of the genes are super abundant, they will tend to hide the other genes that didn't change. So they will appear in your sample to be less represented. So I understand that there are some methods that take that in consideration. Okay. So, well, let's see. Let's see if I find that a good explanation between now and Tuesday. Tamam? Good question, Baris. Good question. Yeah, we should have done this before, maybe. What else?
This was it. This was
Okay,
from
no,
me
I'm just
today.
look at Tunj has the microphone open, so maybe he wants to say something.
So I was thinking maybe the opposite was also can be accepted. No?
What do you mean the opposite?
I'm not good with math, but I mean, we said A and B is low or same, C is high. So if the C is high, A and B appears to be lower
Exactly
than the normal.
Exactly.
So let's think the reverse. A and B is high and C is inaccurate. So would it tell us that C is a bit higher than it's supposed to be because of A and B? Or am I thinking wrong?
Well, you say if A and B, I mean, let's keep A and B fixed first. And if C goes up, A and B seem to go down. If C go down, A and B will seem to go up. At some moment, you don't see, you cannot, I mean, depending on how you analyze it, but the situation is that you cannot distinguish if one is increasing or the other are decreasing. It's kind of a race, no? If one is running faster or the other running slower, what you see is the difference. But I guess then when you can use some other hypothesis like housekeeping gene, if the housekeeping gene seems to go down, then you say, okay, it's not that, it's someone else that's going up. I don't know. I will guess something like that. I don't know if these methods are very, very robust, are very, very, how can I say, not evolving anymore, because what I have seen is that the way to normalize RNA-seq has changed in the last year, and as long as people start developing, I mean, better mathematical tools. So I don't know if we have seen the last version. What I would like you to keep in mind, at least what is the philosophy here. The philosophy is that we have a reality that we cannot observe, and what we measure is a random product of the technology that we use and the biology, and we need to understand that randomness. And this randomness of counts is normally not following a normal distribution. They follow other, they got the binomial or negative binomial and things that we usually don't teach in biology, but I guess we should teach.
Yeah.
Okay.
One more comment, last comment about.
No, that doesn't need to be. You can make a lot of comment.
Yeah, not just the mathematical tools, but also the wet lab tools also does allow a better counting. Like there is a unique molecular identifier now that as a method they ligate to the reads before the sequencing that allows a better quantification of the reads.
I mean, if you have any molecular wet lab procedure that reduce the noise, the variability, it is variable. It is important. Of course, the wet lab mission essentially is to measure values with narrow intervals. No? But there is some variability that you cannot avoid. For example, there is if you take different individuals, there will be variation between individuals that are beyond the technique, just that individuals are different. And here we have another source of noise, which is the splicing, or not splicing, the shotgun of the messengers. The messengers that we read are there is a source of noise, and I don't know how much we can control that. But yeah, I'm assuming, my point is this: even if you do the best wet lab procedures, you still have noise that cannot be avoided. And the question is what we do to get a biological conclusion. Of course, if you had a bad experiment, you're losing your time. Okay, let me be very clear. The correct wet lab procedure are essential part, are necessary condition, but not sufficient. Even if you get numbers measured with very good quality, the conclusion don't came from the numbers themselves. Data is not information. Of course, you need good data. That is no issue with that. We have to do good lab, good wet lab, but it's not the only. It's not the end of the story. It used to be. It used to be the end of the story. It's not anymore. And it will certainly not be in the next 30, 40 years when you are working in this. Okay.
Okay, so about the good data. So I was going to send you an email about, well, the subject is the finals now. Talking about finals. So I was going to send you an email about the FASTQ files.